please start.
Great, thanks very much. Thanks for the introduction and thanks for having me. I feel like year after year over the last decade, I've always tried to make plans to come to Korea in the fall, and because of teaching or kids or something, it's never worked. So I'm sorry I'm not actually there in person this time, but at least I'm glad I get to connect and talk about some physics. So thanks very much for having me. So yeah, the title of my seminar today is SMEFT enough? Is the Standard Model EFT enough? And hopefully that question will make more sense throughout the course of the talk. What I'll be talking about is primarily based on work that I've been doing with Tim Cohen at the University of Oregon, Xiaochuan Liu also at the University of Oregon, and Dave Sutherland, who's now at Trieste. And so this is based on a paper that came out in August, as well as a number of different works that are currently in progress. And so, why interest in the Standard Model EFT or any effective field theory? And the answer is, of course, that these are the sorts of things that give meaning to measurements, right? So that we are in the course of a precision Higgs physics program at the LHC. That is, the LHC upcoming third run, and the HL-LHC will get us Higgs precision to the 5 to 10% level, which is something we never, of course, expected to see at a Hadron Collider. And the host of future colliders, ILC, CEPC, FCCEE, these Higgs factories are proposed to get Higgs precision at the level, the sub-percent level. And so at the end of the day, of course, precision is great, but what you want to do is really understand what it means. So interpreting either agreement with standard model predictions or disagreement with standard model predictions invites an effective field theory framework. Now, of course, that's not the unique way to describe agreements or disagreements. If there are very light degrees of freedom, then they should, of course, be included directly. But anything that is not a propagating degree of freedom appearing in Higgs measurements should be described by an EFT. So there's incredible, just to understand this enormous amount of Higgs data that we'll be collecting over the course of the next 20 years at the LHC alone, really it gives very strong motivation to understanding effective field theories capable of including Higgs physics. And so at the end of the day, the point of this talk is just to address the question, which EFT should we be using, and why would you ever try to make a different choice of an EFT than necessarily the one we've been using? So of course, when you talk about EFT extensions of the standard model that include the Higgs, there's really two options. So one is the standard model EFT, what's been called now the standard model EFT, which is, due really originally to Weinberg in some sense, where you just take the gauge invariant degrees of freedom of the standard model and you include irrelevant operators. And this is an EFT with a very well-defined power counting in terms of the engineering dimension of those operators. And the manifest symmetry, the gauge symmetry, of course, of that is at least in the electroweak sector, setting aside QCD, is SU2 cross U1. But there's an alternative, which is just to use only the manifest long-range symmetries of the standard model, which is electromagnetism. And in that case, in the presence of a real scalar degree of freedom, you could instead construct an EFT that just involved that real scalar degree of freedom and the Goldstones that are eaten to become the longitudinal modes of the W and Z without presuming any relation between them given by SU2 cross U1 invariance. Okay, so this is these days it's often called HEFT for the Higgs EFT. Sometimes it's also called the electroweak chiral Lagrangian of the Higgs, and it's very much motivated, and its power counting is motivated instead in a close analogy with the chiral Lagrangian of QCD. All right. So, there's one question is why bother to study or understand the differences between these EFTs? And I think for me, there's two motivations to really investing in these EFTs. One of them is the sort of in principle point, which is that one of these EFTs describes the theory of nature up to some energy. And so we might as well study it purely from a field theory exercise, simply to understand what its properties are qua quantum field theory. But there's also, I think, maybe even a stronger motivation as practical, which is that these EFTs, they provide meaningful guidance to experimental tests of Higgs properties, and which EFT framework you work in actually has a significant impact on how you interpret the data, because they organize the power counting in different ways. And there's a final reason that this is really just urgent to do, to think about these EFTs very carefully, which is data. And we're actually at the point now where it's not just theorists taking Higgs measurements from the Atlas and CMS collaborations and interpreting them in an EFT framework. Now the collaborations themselves are producing interpretations of these frameworks. So the right panel is just two examples of some recent Atlas measurements, which are interpreted directly in the context of some operators in the standard model EFT. and the left panel is a CMS measurement. Of course, this is just giving you measurements in the context of the familiar kappa parametrization of Higgs couplings, but that actually has a very close relationship to the HEFT basis for EFTs. So in some sense, you can think of it as a HEFT interpretation. So even the collaborations are giving us interpretations of data in the context of these EFTs. And so it's really just important that we understand them as thoroughly as we can. So I think it's inescapable to notice that there's been vastly more progress on the Standard Model EFT, the SU2 cross U1 invariant effective field theory, since the discovery of the Higgs, and that's all across the board. So the precision with which we've computed various quantities at both loop orders and degrees in power counting fits to Higgs data, projections for future measurements at the LHC and future colliders, the development of theorems about the radiative structure of these, the matrices of anomalous dimensions, for example. Extraordinary amount of work has been done in SMEFT, and much less, although some work has been done in HEFT, certainly much less has been done in that context. And I think intuitively, this seems justified because SU2 cross U1 is an apparently good symmetry near the weak scale, and we don't see any order 1 deviation in Higgs properties, so it seems like a good assumption. And so this really just raises the question, this is the animating question for us at the beginning of this research, which is, when is HEFT necessary? Is HEFT necessary at all? Or does the fact that we see approximately standard model like Higgs mean that the SMEFT EFT is the only necessary one for the data that we have? And of course, if the answer to this question were, yes, SMEFT is enough, then I wouldn't be giving this talk. And so what I'll try to convince you of in the remainder of the talk is just how rich and interesting the Higgs EFT is. But to do that, we actually have to draw meaningful distinctions between the EFTs. And although I've laid out to you the ways in which these EFTs are parametrizations in the Higgs sector, the freedom to do field redefinitions without changing S matrix elements actually obscures just the naive differences between these EFTs. In other words, you can easily pass between the two descriptions by doing a field redefinition. And so that really invites the deeper question: what is actually different between these EFTs, and under what circumstances, what UV physics, mapping down to physics at the weak scale, requires the HEFT parametrization and forbids the SMEFT parametrization? All right, so to draw this distinction, we should start out just by defining what we mean by these EFTs in a more formal sense. And so for the purposes of this talk, I'll take SMEFT to be an EFT where we take the 4 scalar degrees of freedom that we normally associate with the SU2 Higgs doublet. And because for simplicity, I'm actually, rather than thinking of them as a complex doublet of SU2, we'll think instead in terms of O4 language, where we're talking about an O4 fundamental. And for the rest of this talk, I'm going to assume custodial symmetry. So breaking custodial symmetry adds some interesting richness to the story, but it doesn't change any of the essential properties. Okay, although extending this whole picture to custodial violation is one of the things we're currently working on. All right, so if I just take the Higgs, the EFT constructed out of an O4 fundamental of scalars, then of course that just means I have four scalars that I arrange into a vector that transform manifestly linearly under O4 transformations. And so naturally, of course, we say in this situation, electroweak symmetry is linearly realized, and good examples of theories written in terms of this parametrization include just the standard model, which are just the marginal and relevant operators involving this O4 fundamental. And then we can also include irrelevant operators, and that gives us SMEFT. And so here I've just given you an example at the bottom of the screen. I know I can't see my cursor, I don't know if you can see it, but at the bottom, here's a SMEFT parametrization where in addition to the marginal and relevant operators, you can add polynomials of the modulus squared of this O4 fundamental. And I should also say, for the purposes of distinguishing between the EFTs, I'm going to ignore fermions and vectors. Really, the distinctions rest in the scalar sector, which is the real scalar degree of freedom we've discovered in the Goldstones. Okay, so for our purposes, we're going to focus on that subset of operators in both EFTs. And the other alternative, of course, is this thing I've called the Higgs EFT, or the electroweak chiral Lagrangian. And the idea is here that we're simply not presuming any relationship between the real scalar H and the Goldstones that make up the longitudinal modes, the W and Z. And the way to package, of course, this into a manifestly O4 invariant language is to assemble the Goldstones into a constrained multiplet that transforms linearly under O4 transformations. But that, of course, that's the constrained multiplet is transforming linearly. The Goldstones themselves transform non-linearly. And so because there's no relation between H and the Goldstones here, electroweak symmetry is non-linearly realized. Of course, this is just a parametrization, and we could use this parametrization also to write down theories like the Standard Model. And so here in this Standard Model line, I just given you the Standard Model in this basis. But you can also then imagine writing down a more general EFT, where you take the kinetic terms for H and the Goldstones, and you tack on arbitrary polynomials in little h, as well as allowing yourself irrelevant operators to appear in the potential. Now, of course, there's a coefficient of the Higgs kinetic term with the square of this polynomial k. It's conventional. That's actually a redundant operator. It's conventional to typically do a field redefinition to set it to 1. But very often you'll find if you're actually trying to explicitly do a matching calculation between a UV theory and an EFT, that you get some non-zero value for this in your natural matching basis. So I'm just going to keep it around for clearer comparison in what follows. Something else I just want to note is both in defining SMEFT and HEFT, I'm truncating it at the two derivative level. Okay. The reason for that is that for most of this talk, I'll develop a geometric picture, and the geometric picture is given by the metric at the two derivative order. It is possible that physics that happens at the 4 and higher derivative order can slightly change what I'm going to describe, but again, not in an essential way. All right. So a simple observation, which was made very concrete by Alonso, Jenkins, and Manahar in a series of papers a few years ago, is that, of course, a SMEFT EFT can always be written as a HEFT. We have the absolute freedom to do that. And it just amounts to doing a field redefinition by which we take the O4 linear realization of the Higgs in SMEFT, and we write it in terms of the HEFT coordinates. And if we simply do that, then we can take any SMEFT Lagrangian and write it in terms of the HEFT coordinates, and we'll have a perfectly valid Lagrangian that is as predictive as the SMEFT parametrization before we did the field redefinition. And the way you know that you actually secretly had a SMEFT that was organized by the SU2 cross U1 invariance is that if you write it in terms of the HEFT variables, you end up with correlations between the real scalar H and powers of the Higgs EFT at every order. In all of these polynomials, these irrelevant operators, H and V are correlated order by order, okay, because they came from a doublet. So we can, SMEFT, that means SMEFTon is a proper subset of HEFT, and any SMEFT can be written as a HEFT. So the question that's interesting is really the other way. What are the HEFTs that cannot ever be written as a SMEFT? Do we care about them? Are they consistent with data? And does this mean we need to take HEFT more seriously? Okay. So the first step you would make in addressing that question is just trying to answer, well, how can I take it the other way? When can I take a theory in a HEFT basis and not for some reason write it as a consistent SMEFT theory? And so maybe you can just tell by eye. Maybe, we said that if we have a SMEFT in the HEFT parametrization, it has some correlations order by order between V and H. So here I'm just giving you an example. Here's some Lagrangian in the HEFT basis, and it looks like it's broken this order by order relation between H and V because it has these funny powers of 3/4. Okay, so if you could tell by eye, you might say, clearly this is HEFT. And of course, if I were there at KIS in person, this is the point in the talk where I would ask everyone to raise their hand if they thought it was a HEFT, raise their hand if they thought it was a SMEFT. That's a fun question to ask. So you should just answer for yourself if you think this is a HEFT EFT or a SMEFT EFT. But the problem is, of course, we have the freedom to do field redefinitions. So it looks like a HEFT, but let me just do the following polynomial field redefinition of little h. If I perform that field redefinition, I find, in fact, that this EFT I've written for you in the HEFT variables, it's not even secretly a SMEFT. It's actually secretly just a standard model. Okay, so that's a nice demonstration that there's really no inspection of these Lagrangians that will tell you if it is a HEFT that can or cannot be written as a SMEFT, because field redefinitions obscure the differences. So that means we need some more robust way of deciding when we have a HEFT or a SMEFT. And hopefully, not only can we have a more robust distinction, but by developing that distinction, we could start to learn what is the sort of essential underlying physics that distinguishes the two. Okay. So some very interesting progress was made on this question early in 2019 in a nice paper by Adam Falkowski and Riccardo Rattazzi, as well as a nice paper by Spencer Cheng and Marcus Ludi around the same time. And they made the following claim, which is that, which is that HEFT can only be written as SMEFT when the potential written in terms of the SU2 doublet H is analytic at the origin. Okay, that corresponds in terms of the field coordinate little h, the real Higgs, that would be 8 little h at minus v. Okay, that's big H, the doublet is at the origin. So the claim is analyticity of the potential, when written in terms of this doublet parametrization, tells you if you have a SMEFT or not. And they were able to, this claim was made robust in a very interesting way, actually using inelastic scattering amplitudes in the EFT parametrization. So the basic idea in their paper was, let's imagine you took a toy model where you saw at the LHC a deviation, calling it here delta 3, in the Higgs cubic self-coupling relative to the standard model. And that was the only difference you saw. So basically the quartic was in agreement with the standard model, but the cubic disagreed by some amount, delta 3. And so if you try to write that relationship in terms of the SU2 doublet big H, you notice that the potential arranges itself into a standard model-like piece, plus a piece that's proportional to this deviation delta 3, but that deviation multiplies a function of the doublet H that is non-analytic at H is equal to 0 because of the square root, okay? And so there's a physical consequence of this, which tells you that such a theory must be described by HEFT and cannot be described by SMEFT, which is that the non-analyticity at the origin in these SU2 doublet coordinates actually gives you perturbative unitarity violation in scattering channels between two Goldstones and any number of Higgses. So if you sum over the inclusive processes over which you produce any number of Higgses, that there's unitarity violation that only depends logarithmically on this coefficient. Okay, so the unitarity violation is by 4 pi v, square root of f is 4 pi v, with only logarithmic sensitivity to the coefficient. All right, so that's a very strong indication that your EFT blows up by 4 pi v and is a sort of HEFT-like EFT as opposed to SMEFT, which in principle can be valid to higher scales. Now, although this isn't our work, I do want to pause to actually go through their argument briefly because it's a very useful application of unitarity bounds and one that's somewhat different, I think, from the unitarity bounds we're used to thinking about in elastic 2-to-2 scattering. So the basic observation that they made to make this point concrete was that you could basically think of perturbative unitarity as the requirement that the phases in the S matrix be less than or of order pi. The assumption of pi is important for their NDA scaling. So we'll assume the phases are less than order pi. And in the Born approximation, then of course that just amounts to a bound on matrix elements for normalized states, okay, between the transfer matrix. So normally we take that statement and we set bounds, perturbative unitarity bounds, by considering elastic 2-to-2 scattering processes. But what they do instead is they consider the partial wave expansion of the inelastic processes of any two pions going to any number of Higgses. And the corresponding requirement of perturbative unitarity is that the sum over all of these amplitudes not be greater than pi squared. Okay, so it's just a natural insertion of a complete set of states leads to that statement. And so they go ahead and they try to evaluate the left-hand side in a little more detail, making a few approximations, including assuming massless phase space in the final state and approximating the amplitudes for n Higgses by the leading piece in their expansion, which is the contact term. And indeed, what they find is that these amplitudes depend, they have an exponential unitarity violation at 4 pi v. And so therefore, the scale of unitarity violation only depends logarithmically on the coefficient of this non-analytic term. Okay, so this is a very strong statement that if there's a potential that has a non-analyticity at the origin in the SU2 doublet coordinates, then that EFT should be a HEFT and cannot be written as a SMEFT. All right, so that's a very interesting claim about what defines a HEFT rather than SMEFT, framed in terms of scattering amplitudes. There's been a second approach to drawing some firm distinction between HEFT and SMEFT, which is instead sort of pursued via the geometry of the effective field theory. And this is the picture that I want to expand on for the next bit of the talk. So this is also, anyone who's used to thinking about nonlinear sigma models, of course, recognizes that you can classify EFTs based on the geometry of the scalar manifold, that the two derivative terms in the scalar part of the action define a metric. And we can study the properties, of course, of the metric and the scalar field manifold to understand invariant properties of the theory. Okay. So the application, this of course is a very old observation going back decades, but its application to HEFT was again first made by Alonzo, Jenkins, and Menahar in this pair of nice papers about 5 years ago. And so what's the punchline? Well, the basic idea or the basic observation is that there's a simple geometric picture for an EFT that's described by SMEFT. Okay, so what's the essential observation? Well, the essential observation is to be a SMEFT, there has to be a point on the EFT manifold where the full symmetry is restored. So if we're thinking about the standard model EFT, that would be an O4 invariant point. O4 invariant points are a little hard to draw on a two-dimensional slide, so I'm just going to give you this cartoon here with an O2 example, okay, which is a circle fibered over the H direction, the real scalar direction, okay? And so if it's a SMEFT, then there has to be an O2 fixed point on this parabola, because at that point, in these coordinates, the pi or Goldstone coordinates being circles around the parabola, and the Higgs little h direction taking you up along the parabola, the existence of an O2 fixed point means there is a point on the manifold where, of course, your O2 transformations don't do anything, okay? So that's what it means to have an O2 fixed point. And then as you go away from that fixed point, the size of the O2 orbits depends on the value of little h, okay? So if, of course, the real O4 example has an S3 at every point on this Higgs degree of freedom. Okay, so then, of course, if you just write down the HEFT parametrization of an EFT and you want to know, is this secretly something I could instead write as a SMEFT? Because a SMEFT has an O4 fixed point on the scalar manifold, that means there has to be a point on the manifold where this function f that lives out in front of the kinetic term of the Goldstones is 0. Okay, it is at that point, indeed, that you're at this invariant fixed point where O4 transformations don't move you anywhere on the manifold. All right, so they came up with a very clear criterion that HEFTs can be written as SMEFTs if this function f vanishes at some point on the scalar manifold, and that was their distinction between SMEFT and HEFT. And conversely, they were able to then understand a little bit more about theories, EFTs, that could only be written as HEFTs and not as SMEFTs. And it follows directly from the condition I just gave you. Conversely, if there is no point on the scalar manifold where this function f vanishes, there is no O4 fixed point. And so there's no point about which you could expand in SMEFT coordinates that are, manifestly linear transforming under SU2 cross U1. All right, so you should think of that as being some scalar manifold with a hole in it, where the hole is punching out what would have been the O4 invariant fixed point. All right, and so this was their criteria for HEFTs that could not be written as SMEFTs, which is that there's simply no O4 invariant fixed point on the manifold, as parametrized by the fact that this function f does not vanish anywhere in the EFT. So at this point, there's a lot of questions, right? So the Rattazzi-Falkowski criteria for HEFT is a statement about scattering amplitudes and criteria of the properties of the potential at the origin in the SMEFT parametrization. The Alonzo-Jenkins and Manahar geometric perspective is a very different one. It has to do entirely with the properties of the two derivative sector of the theory. It has to do with the properties of the metric, and has a very simple criteria. But these two criteria for what defines a HEFT or a SMEFT, they are totally non-intersecting. And so, of course, it invites the question, what is the complete picture, right? What is the absolute total definition of a theory that is a HEFT that cannot be written as a SMEFT? And then the further question of what sort of UV physics gets you there? What sort of UV physics gives you a HEFT that cannot be written as a SMEFT? And so that's what I'm going to answer in the rest of our time. All right. So what I'm going to do is I'm first going to try to develop the complete picture, continuing in this geometric language of Alonzo, Jenkins, and Manahar. But at the end, I want to bring it back to the scattering amplitude picture that was developed by Falkowski and Rattazzi, because at the end of the day, all of the pictures tie together in a very nice way. So the first thing you might worry about with the Alonzo, Jenkins, and Manahar criteria is whether it's actually complete, whether there are HEFTs that actually satisfy the fact that f vanishes somewhere, but still can't be written as SMEFTs. And the reason you might suspect that there's a problem, an incompleteness with their definition, is that we already know that if we have a SMEFT and we write it as a HEFT, there are correlations at every order in that EFT between H and V. That's an infinite set of conditions, right, that relate the coefficients of this EFT. But that infinite set of conditions is not, here in Alonzo, Jenkins, and Manahar have one condition, which is that this function f vanish somewhere on the manifold to be a SMEFT. But we know secretly there should be an infinite set of conditions for your theory to actually be SMEFT. And so where did that infinite set of conditions come from? So the answer is there's another pathology, possible pathology in your scalar manifold that would tell you that you have to be a HEFT. Instead of just having a hole that precludes the O4 invariant fixed point, you could also have a cone or a cusp. But before I get into that second example, first I just want to give you a little bit more intuition about the example that Alonzo, Jenkins, and Manahar identified, which is that you end up with a HEFT because your O4 invariant fixed point is missing from the manifold. So let me give you a simple toy model, okay, and a simple way of thinking about why this happens. And the answer is, of course, the O4 invariant fixed point is missing from your manifold if something else in the ultraviolet theory also broke the symmetry, okay, also broke SU2 cross U1. So this, of course, could be any extension of the standard model that has additional electroweak scalar multiplets in the UV. But to see what's going on, it's actually easiest just to think about a toy model, a sort of 2 abelian Higgs model, where you just think about 2 Higgses charged under U1 gauge symmetry. So this is a theory where the global symmetry we care about is O2. So it maps exactly onto these nice manifold pictures I've been showing you. So you can just think about this theory. It has 1 U1 gauge symmetry, 2 Higgs scalars. I'm going to give them different charges so we don't have to worry about a choice of basis. And now you can just imagine the potential is such that both Higgses acquire vacuum expectation values, so they both break the symmetry. But now you can imagine arranging the potential and the kinetic term such that the spectrum of massive degrees of freedom contains one approximate light U1 complex multiplet of a light real scalar and pseudoscalar, and then a pair of heavy scalar fields. And so now, of course, we can integrate out the heavy scalar fields to get the EFT of the light scalar fields. And in this toy model, that's the analogy of integrating out some heavy doublets, for example, and looking at the EFT of the standard model Higgs. And what you find when you carry out this exercise is that indeed this function f you get in the HEFT parametrization when you integrate out the heavy fields, it has the form of the sum of 2 squares, which means that in general, in fact, it's non-zero everywhere on the scalar manifold, okay? It's sum of 2 squares shifted by constants. So that's never 0 anywhere on the manifold. And so indeed, that means there's no point where this function vanishes, and therefore there's no, in this example, O2 invariant point, okay? So a good intuition for when the invariant fixed point is missing from the manifold is that something else broke the symmetry by some amount in the UV. I want to give you another visual way to think about this that actually turns out to be extremely useful if you think about examples that relate more closely to the standard model, which is that if something else breaks the symmetry, and if it's a perturbative theory, that something else are some other scalar degrees of freedom. And so in that case, you can think both about the full manifold of the UV theory, that full scalar manifold, including both the heavy and light degrees of freedom. And in that case, if you're only working to 2 derivative order, then the EFT is actually a submanifold of that full UV manifold, okay? And so now you can ask about how the EFT submanifold is situated within the full manifold. And the condition that the EFT contain the invariant fixed point means basically that if you think about the full space of the scalar manifold, it has 2 interesting points in it. It has an invariant point where the symmetry is restored in the UV, okay? That's the O4 fixed point in the standard model. And it also has some minimum. It could be global or local, but that's the minimum that we associate with the vacuum in which electroweak symmetry is broken. So both of those points necessarily exist on the scalar manifold of the full theory. So now what you're interested in whether your EFT is a HEFT or a SMEFT, is now a question about what slice of that full manifold is the submanifold of your EFT. And you can either end up in one of 2 situations. The submanifold that's your EFT either can include both the fixed point and the minimum. Okay, in that case, the fixed point is part of the EFT manifold, and it should be a SMEFT. But it's also possible that, that the scalar manifold of the EFT does not include the invariant fixed point. And in that case, of course, if you just looked at the EFT manifold, it would not have the fixed point and it would be a HEFT. And so this is just a cartoon of the simple example I've given you, where the left panel is showing contours of the full manifold. The left and right panels are both showing contours of the full scalar manifold. The left panel is parameters where the mass squared of the heavy field is positive. The right panel is where it's negative, and so it acquires a VEV. And there's lots of lines here because we considered lots of different bases for this theory. But the one you should pay attention to is the light blue or cyan line. And in the left, that goes from the point 0, 0 on the left part of the frame to the black dot, which is the global minimum. And so that means the EFT submanifold, in fact, includes both points and is a SMEFT. But in the right panel, where the UV field has a negative mass squared and so acquires a VEV and also breaks the symmetry, the EFT submanifold that runs through our minimum, the place where we live, actually never itself intersects the invariant point at 0, 0. And so that EFT submanifold doesn't contain the O2 invariant point. And so it must be a HEFT. So this just gives you a nice graphical intuition for the statement that if there's another source of symmetry breaking, then it precludes the invariant fixed point in the EFT submanifold. All right. So that's just some more understanding for this nice situation that Manahar, Jenkins, and Alonso worked out. But now, as I said, that can't be the entire story, because there are really an infinite set of conditions if you have a SMEFT and you've written it in HEFT parameters. And the Alonso, Jenkins, and Manahar condition is a single condition on the EFT. So the question is, where does the other infinite set of conditions come from? And the answer is, there's another pathology on the EFT manifold that would prevent the EFT from being expressed as a SMEFT. And that's simply that, nominally speaking, the invariant point exists on your manifold, but there is a cone or a cusp there, okay? And it turns out that that requires a stronger set of conditions than just this function f vanish or not at the invariant point. And indeed, you can't simply look at this function f and the HEFT parametrization to diagnose the presence of a cone or a cusp, because at the invariant fixed point, the HEFT parametrization, it's like polar coordinates, so it degenerates at this point. And so simply inspecting the function is not enough to tell you whether or not the theory is truly a HEFT. But instead, you can do something just like we do in GR, which is you can diagnose the existence of a singularity at your nominal fixed point by looking at various invariants. So of course, you can construct the Ricci scalar for this EFT manifold. You can also simply look directly at the potential, which is another scalar invariant. But crucially, you can in fact construct infinite classes of invariants, which just consist of even powers of covariant derivatives of either the Ricci scalar or the scalar potential. All right. And at the end of the day, if all powers of those derivatives, including no derivatives of the Ricci scalar and the scalar potential, are finite at the O4 fixed point, then indeed you can write HEFT as SMEFT. And in fact, that finiteness condition on that infinite set of operators gives you the requisite infinite set of conditions that we saw just by trying to write a SMEFT as a HEFT. So it very nicely completes the picture. But of course, if any of those quantities is infinite at the O4 fixed point, then indeed there is some sort of singularity, typically a cone or a cusp, and the SMEFT coordinates are not actually a valid description of the theory. The theory must be written as a HEFT. So of course, what physical situation leads us to this case? We've already seen that an extra source of symmetry breaking leads us to a hole, so the fixed point is missing. So what UV physics leads us to the situation where instead there's a cone or a cusp at the nominal fixed point? And of course, this is also familiar to anyone who spends their time studying supersymmetric moduli spaces, for example, is that integrating out massless degrees of freedom typically give you this type of singularity on your low energy manifold. So simple examples of this class is anytime a field becomes massless at the point where electroweak symmetry is restored. So I'll just give you a simple example here, which is consider some chiral fermions that you pair in such a way that you could write down a vector-like mass for them if you wanted to. And so, of course, if these fermions have a vector-like mass, well, in fact, regardless of whether or not they have a vector-like mass, if you integrate them out, you'll find, in fact, this function f in the HEFT parametrization vanishes at the invariant point. And so by the original Alonso, Jenkins, and Manahar criteria, it's okay. This should be a SMEFT. But now you can compute the Ricci scalar, and you find that, I'm just giving you the truncated version here for simplicity, it goes like 1 over the vector-like mass squared. So of course, if you set the vector-like mass, if you take it to 0, which means these fermions are now only acquiring their mass from electroweak symmetry breaking and become massless at the point where electroweak symmetry is restored, then obviously you see the Ricci scalar blows up. Okay, so if these fields acquire all of their mass from electroweak symmetry breaking, they give a singularity at the invariant fixed point, and that's nicely reflected in this geometric criteria. All right, so that actually gives us, at least on the geometric side, that's enough now to give us a complete set of criteria within the assumptions I've made, operating with custodial symmetry and at the two derivative level, for when you have an EFT that you can always choose to write as a SMEFT, okay? And now the full set of criteria is the original Alonzo-Jenkins and Manhart criteria, which is there's a point at which this function f vanishes. That's the O4 invariant fixed point. But now you also require that the metric is analytic at that point, which is to say that this function f, for example, admits a Taylor expansion, and that's a convergent Taylor expansion. And that's reflected in the fact that any powers, even powers of covariant derivatives of the Ricci scalar, including 0 powers, is finite there. And you also have a criteria, an analogous criteria, not just on the two derivative parts, but on the potential, the 0 derivative parts, which is that the potential admit a convergent Taylor expansion, and indeed, any even powers of covariant derivatives of the potential also be finite at that point. So it turns out this full set of criteria now captures all of the situations in which a theory, an EFT, can be written as SMEFT in geometric terms. And because it's framed in terms of scalar invariant quantities, you can determine this criteria, whether it's satisfied in any basis you like. It's not disrupted by field redefinitions. Okay. So that's a nice uniform geometric set of criteria that lets you know if your EFT can be written as a SMEFT, or if it can't, instead, if it must be written as a HEFT. And that also these criteria, hopefully, as I've explained, provide there's some clear physical scenarios in which indeed you fail some of these criteria and your EFT must be a HEFT. So at this point, I think it's actually sufficient to really emphasize that HEFT is necessary if we want to describe Higgs data at the LHC. Because there's a simple example that's consistent with all known data and all direct searches, whose effective field theory must be a HEFT by the criteria I've given you. And the simple example is just a singlet scalar field that requires all of its mass from electroweak symmetry breaking. Now you might object, of course, famously, there's no symmetry that is restored when the mass of the scalar goes to 0. So of course, I also am allowed to include a bare mass in addition to whatever mass it acquires from the Higgs. And that will change this picture a little bit, but we'll get to that in a moment. For now, if you just consider just a singlet scalar, it of course could have self-interactions. Those aren't going to be important for what I'm going to say. If you just consider the quadratic and linear terms that are allowed by the symmetries coupling it to the Higgs, then of course we know from LHC data, this scenario is totally unconstrained if the mass of the scalar is more than half the mass of the Higgs. If it's less than half the mass of the Higgs, then of course the Higgs can decay into pairs of this, pairs of the singlet. But if it's heavier than half the mass of the Higgs, there's no direct bound. Okay, so there's a large parameter space where there's no constraints. And now, of course, you can go ahead and follow this prescription. You can compute the effective Lagrangian by integrating this thing out, both the 0 derivative and the 2 derivative effective Lagrangian to all orders. And so you can go ahead and you can compute in the HEFT parametrization these functions f and k. And what you find is they're both nicely behaved and analytic, but the potential that you obtain is non-analytic at the invariant fixed point. And if you compute the Ricci scalar for this theory, it blows up at the invariant fixed point. So that's just the hallmark of the fact that the scalar becomes massless when electroweak symmetry is restored. So this is a theory that must be written as HEFT. Okay, it does not admit a convergent SMEFT expansion, and it's totally consistent with all allowed data. So, from my perspective, HEFT doesn't require something crazy to happen like some other strong physics breaking electroweak symmetry. HEFT could be required by something as simple as a scalar acquiring its mass from the Higgs. All right. But I also want to emphasize, even if it requires some of its mass from the Higgs and some of its mass from somewhere else, even if you end up in a situation where the SMEFT parametrization might exist, so you would be allowed to write down a SMEFT description of the resulting EFT, HEFT is still very often the best way of describing the data in a way that I'd like to make precise. Okay. So the message here is there are also just situations, even when both HEFT and SMEFT exist, that HEFT is by far the better way of describing data. And so to drive this point home, let's just consider the singlet scalar example again. But now let's imagine it gets some of its mass from the Higgs and some of its mass from a bare mass term. Okay, so we can repeat this procedure that I just did in the last slide, which is integrate out this scalar to get the effective Lagrangian for the Higgs degree of freedom. And what we find is indeed there's this non-analyticity in the potential, and there's the functional form of the two derivative terms that I've written here. So now we can carry out the following exercise. We actually have the full exact results for the effective Lagrangian at the 0 and 2 derivative order. But now I can do two things. I can take these results and I can expand them in a HEFT parametrization, and I can also expand them in a SMEFT parametrization. And of course, both of them formally will include an infinite number of terms because I'm Taylor expanding these functions in terms of those coordinates. But now we can just ask the question, how far do you have to go in each of those expansions before that parametrization gives you good agreement with the data? And the answer is, very often, HEFT gives you good agreement with the data much sooner in terms of an expansion in the coordinate than the SMEFT parametrization does. All right, so let me make that more precise. So we'll take these exact answers that we get from integrating out this scalar that gets some of its mass from the Higgs and some of its mass from the bare mass term. And we can imagine either expanding that result in a sort of HEFT coordinate, okay, which is basically an expansion of little h around the electroweak symmetry breaking vacuum. Or we could expand in terms of the SMEFT coordinate system, which is an expansion in terms of the doublet mod h squared. Okay. And now what we want to do is we want to look at both of these expansions and basically consider the radius of convergence of each expansion. And the radius of convergence is usefully parametrized in terms of a ratio, which is just how much mass does it get independent of electroweak symmetry breaking relative to how much mass it gets dependent from electroweak symmetry breaking. So this parameter R is just the ratio of how much mass does it get not from the Higgs versus how much mass does it get from the Higgs. And the key point is that as a function of this parameter R, okay, how much mass is coming from electroweak symmetry breaking, the radius of convergence of the HEFT expansion is always larger than the SMEFT expansion, because the SMEFT expansion is an expansion around the origin, and it's always going to hit the branch cut on the complex H plane at a smaller radius than the HEFT expansion, because the HEFT expansion is an expansion around R vacuum where electroweak symmetry is broken. Okay, so the radius of convergence of HEFT in this case is larger than SMEFT, and not just the radius of convergence, but even if both expansions converge at R vacuum, all right, it's possible that you can go fewer terms into the HEFT expansion than the SMEFT expansion to agree with the data. And so here's just a cartoon demonstrating that. So again, this parameter R is telling you which EFT is good. So if R is 0, that means you get all of your mass from electroweak symmetry breaking. And that's the situation we've already described where you simply cannot write down a SMEFT. There's no analytic expansion in SMEFT coordinates, but you can write down a HEFT. The next interesting range of R is when R is between 0 and 1. In that case, a SMEFT expansion exists, you can define it, but it doesn't converge at R vacuum because the radius of convergence doesn't extend from the symmetric point where electroweak symmetry is restored to the physical vacuum that we live in. So even in that regime, you still can only use HEFT because SMEFT will not converge. Now, of course, once R gets larger than 1, now the particle is getting more than half of its mass independent of electroweak symmetry breaking. So at that point, the SMEFT expansion exists and can converge at the observed vacuum. But the important point here is that even if R is greater than 1, even if the particle is getting the majority of its mass independent of electroweak symmetry breaking, until it's getting almost all of its mass independent of electroweak symmetry breaking, the HEFT expansion still converges much faster. And so these plots that I'm showing you here, they're just examples of the deviation in the Higgs cubic and quartic self-coupling in this example I've given you as a function of the order in the HEFT or SMEFT expansion that you go, and how quickly those expansions at a given order converge to the actual deviation given by the full effective Lagrangian. And so of course, in the upper two, when R is 5, so almost all of the mass is coming from something other than electroweak symmetry breaking, then you can go a few terms in the expansion in either EFT and match the actual result. But if R is 2, that still means the particle is getting 2/3 of its mass squared independent of electroweak symmetry breaking. The HEFT expansion still converges almost immediately, but the SMEFT expansion, you have to go to fairly high order before you begin to actually match the true correction. And if you translated this into an actual physical scenario you could expect to see at the LHC, you would see some deviation in Higgs properties. You could try to fit it using SMEFT, and you would draw some conclusions, for example, about the underlying theory and the scale of new physics. But the demonstration here is that unless the degrees of freedom that gave you those corrections are very heavy, much above the weak scale, you actually will be misled by your SMEFT parametrization of the data, whereas a HEFT parametrization will give you a much sharper agreement with the real underlying physics. All right, so that's just an illustration of even when both EFTs exist, HEFT can be the superior parametrization. All right, so that's it for the geometric picture, distinguishing HEFT from SMEFT and trying to justify to you why HEFT should be interesting for the LHC. But I want to bring it back now.
Excuse me, Sahei.
Yeah.
I have one question about your singular scalar model.
Yeah.
So in your model, you assume G2 symmetry, so you exclude the S times H dagger H.
No, I don't. Manifestly, in this example that I've given you.
Yeah.
Oh, sorry. Good. Let's see.
So let me. So can I finish my question?
Sure.
So
sure.
suppose we include the SH scale term, and then after electric symmetry breaking, there will be a mixing between the standard model Higgs and the singular scalar.
Yeah.
So the observed Higgs boson, 125 GeV Higgs boson, might have some small mixture of the singular scalar or whatever. In that case, what happens to SME? So I guess SMEFT is not
good. So actually, it turns out
adequate.
qualitatively. So yeah, good. So the example I've given you here indeed has an unbroken Z2, and so the corrections that I've computed all occur at one loop. All right, and so everything I've told you about HEFT versus SMEFT is something you can conclude from looking at the one loop effect of Lagrangian. Now consider the case that you've mentioned. Let's say, for example, you start with a Z2, but it's spontaneously broken by a VEV of S. That would also give you then a linear coupling between S and mod H squared.
Right.
Good. So that would be the same as your example. So then, in fact, then you would see the exact same physics, but it would occur at tree level. You wouldn't have to even work as hard, right? You could integrate out the scalar at tree level, and you would find the same qualitative conclusion that I've told you, which is that if the bare mass is 0, there is simply no SMEFT parametrization, even though the scalar becomes massive. Okay. If the bare mass is non-zero, but is less than half of the mass that acquires from electric symmetry breaking, then SMEFT exists but does not converge. And if the bare mass is non-zero but more than half of the mass, then both HEFT and SMEFT exist. But indeed, unless the bare mass is quite a few times larger than the electric symmetry breaking piece, the HEFT parametrization converges much faster. So in fact, and so we in the paper I just picked this example for completeness. In the paper we work out both cases in full detail. It's a great question. Yeah, of course, great question. Thank you. All right, very good. All right, so here just the point is that the convergence, even if you're allowed to write down both EFTs, unless the particle is quite a bit above the weak scale, acquiring almost all of its mass independent of electric symmetry breaking, HEFT is the best way to understand what the data is actually telling you. Okay, so now I just want to finish by bringing you back to the amplitudes arguments, which is how Falkowski and Rattazzi tried to define when you had to have a HEFT that couldn't be written as a SMEFT. Because at the end of the day, we should somehow be able to see in this geometric picture I've given you, we should be able to connect that to this amplitude-based picture, a unitarity violation of Falkowski and Rattazzi. And so to do that, I want to lean on, again, an observation that is very old to anyone who works on nonlinear sigma models, but was made in the context of HEFT, again, in these nice papers by Alonso, Jenkins, and Manahar in 2015, which is that, of course, you can write on your EFT, you can write your scattering amplitudes in terms of geometric quantities on the scalar manifold. And indeed, the example that was given by Alonso, Jenkins, and Manahar was if you just consider the scattering amplitude for 2 Goldstones into 2 Higgses, the leading piece in Mandelstam S is proportional to the Riemann tensor, where you take 2 of the legs along the Goldstone direction and 2 of the legs along the Higgs direction, plus a piece that corresponds to covariant derivatives of the potential, again, 2 with respect to the Higgs and 2 with respect to the Goldstones. And that gives you the leading in Mandelstam S and the subleading in Mandelstam S parts of the amplitude. And those, of course, are invariant quantities, suitably invariant or covariant under field redefinitions. And so there's a sense in which the scattering amplitudes expressed this way, they measure the local curvature. They basically measure the sectional curvature computed from Riemann, and also the sort of scalar equivalent in the scalar potential. So that's interesting. That at least gives you some expectation that there's a way to see the geometry and the amplitudes, but there's a problem, an apparent problem, which is that we measure the curvature. We are doing scattering around our vacuum where electroweak symmetry is broken. So that's the point where big H is equal to V and little h is equal to 0. And this question about whether the geometry gives you a SMEFT or a HEFT is a question not about that point, but is a question about the invariant point, which is far away. And so given that scattering amplitudes measure curvature in the broken phase in our vacuum, how do we get information from scattering amplitudes about the properties of the manifold way far away at what would be the invariant point? Okay, so that's the question. And understanding that turns out to be very interesting. So the first thing I just want to mention is this sort of parametrization of these amplitudes was just written down in this nice paper by Alonso, Jenkins, and Manahar, but you can make it more systematic very easily. And the basic idea, again, familiar for those who work on nonlinear sigma models, is just to work in terms of geodesic coordinates. So to use the exponential map and its inverse to write your, to transform your field as a scalar on your curved manifold into a degree of freedom living on the tangent space expanded around at some point on the manifold. And so that's a well-defined procedure, and it's one in which your original Lagrangian in terms of your scalar coordinates on the manifold naturally in terms of the geodesic coordinates takes on a form where the coefficients of different terms in the Lagrangian are indeed the components of the Riemann tensor and the Ricci scalar and its components and covariant derivatives of the scalar potential. And so this is just a nice way to express your Lagrangian in a way that manifests geometric quantities in the Lagrangian couplings. So you can always have the freedom to do this. And then, of course, if you, in this coordinate system, you go ahead and compute your scattering amplitudes, then they naturally have the form of some dependence on the Riemann tensor, covariant derivatives of the scalar potential, and so on. Okay, so there's a very systematic way to understand how all of your scattering amplitudes can be written in terms of geometric quantities evaluated at our vacuum. All right, that still doesn't tell us how we're going to be able to, using scattering amplitudes, measure properties not of the curvature at our vacuum, but of the curvature at this the O4 invariant point. Okay, but now you can make the following interesting observation. So we've said that if the theory must be written as HEFT, it's because there is some geometric singularity or some non-linearity, or the O4 invariant fixed point is missing entirely. And now what that means, practically speaking, is if that's true, for example, let's imagine that the potential is non-analytic at the O4 invariant fixed point. So the theory has to be a HEFT. Well, if that's true, then if you take the potential and you write it in a Taylor expansion in terms of coordinates around our vacuum, if you evaluate that at the O4 invariant fixed point, so little h is equal to minus v, that Taylor expansion, of course, cannot converge. And similarly, that Taylor expansion not converging, also two derivatives of that expansion with respect to the Goldstone geodesic coordinates also can't converge. So that non-convergence you can translate into the failure of the ratio test. And so the failure of the ratio test implies that there is some order in the Taylor expansion at which successive orders in the Taylor expansion, successive coefficients, are larger than the previous coefficients multiplied by some powers. Okay, so that's just a statement that a Taylor expansion of the potential around our vacuum doesn't converge at the O4 invariant fixed point. All right. Now we can actually use that observation to look at scattering amplitudes and reproduce the Falkowski and Mutazzi argument. And the basic idea is, you take the inclusive scattering amplitude of two Goldstones into any number of Higgses. Okay, so that's the sum over all of these amplitudes squared with integrated over phase space. And you can now, let's again imagine that it's dominated by contact terms coming from the potential. So you can expand the potential in its Taylor series. But now the fact that the potential is non-analytic at the O4 invariant fixed point meant that we had this failure of the ratio test. And so you can bound the inequality by instead replacing it using information from the failure of the ratio test. So that separates out all of the S-independent coefficients. And you're left over with a series that is the Taylor expansion of an exponential. And so basically what you get is the statement that if the potential is non-analytic at the origin, this scattering amplitude into any number of Higgses indeed has exponential unitarity violation by 4 pi v, and therefore is only logarithmically sensitive to the coefficient of the non-analyticity. But now you can reproduce this same argument, not just with a problem in the potential, but also, for example, with the pathology in the Ricci scalar, or in any covariant derivatives of the Ricci scalar or the potential. And so in this way, you can connect exactly the geometric criterion that I presented to this observation of Lakowski and Rattazzi that the scattering of two Goldstones into any number of Higgses, that inclusive inelastic process, exhibits unitarity violation by 4 pi v. All right. And so in some sense, these inelastic scattering amplitudes, these sum over many processes, even though any one of them is only probing local geometric quantities at our vacuum, the sum over all of them in some sense begins to reconstruct the geometry at the O4 invariant fixed point. And this is how you get access to the properties of the manifold, even though it's far away from our vacuum. All right, so that brings me to the end. So just some trying to tie it all up. We've covered a lot of different ground, but the basic message here is that there is really a universal geometric way of determining what EFTs can only be written as HEFT versus which ones could be written as SMEFT. The key, of course, is not only is there an O4 invariant fixed point on the EFT manifold, if there's no such fixed point, if there's a hole, then it must be a HEFT. But even if that point nominally exists, yet the manifold is singular there because of a cusp or a cone, all of those cases require you to use a HEFT parametrization. But moreover, even if the fixed point exists and everything is smooth there, it can very often be the case that a HEFT parametrization, depending on the curvature around that area, a HEFT parametrization can give you a much better fit to the data than using the SMEFT parametrization. And I've tried to not only give you these sort of geometric conditions, but also connect them to very simple physical scenarios where holes are coming from extra sources of symmetry breaking. These cones or cusps are coming from particles that are getting their mass from electroweak symmetry breaking. And these smooth manifolds that nonetheless have a lot of curvature are coming from integrating out particles that get at least about as much of their mass from the Higgs as they do from another source. And so these observations, and the observation that integrating out a singlet scalar that gets all of its mass from a Higgs requires HEFT, but is totally consistent with all LHC data, that really drives home the fact that we shouldn't just be concluding that the data that we have tells us that SMEFT is a good EFT parameterization. That HEFT actually, in some cases, is required to parameterize data that's consistent with everything else we know. And then the last point is, at least what I find fun about this picture is now there's a way to combine all of these approaches to understanding the distinction between the EFTs, whether it be geometric or from scattering amplitudes. And the ultimate lesson is that these inelastic scattering amplitudes are actually probing the geometry of electroweak symmetry breaking, because they tell us not only about the vacuum where we live, but in fact, they tell us about the properties of the manifold at the O4 fixed point. So to me, the lesson is HEFT is actually a very interesting and rich EFT, and it deserves at least as much attention as we've been giving to SMEFT as we look forward to Higgs data in the coming decades. So thanks very much for your time and for the opportunity to present this work.
Thank you very much. So any question?
So I have a question. So it seems to me that the SMEFT assume you have just a single source of the electroweak symmetry breaking. So suppose you have two sources of the electroweak symmetry breaking. For example, 2x doublet model, or you can have one standard model Higgs doublet and some other representation of SU2 whose neutral component get the non-zero value and contribute to the electroweak symmetry breaking. And in that case, I guess Higgs EFT is still probably applicable.
Yes, yes. And so we in the paper, it's a great question. It's a great observation. We work out both examples in the paper. So I can tell you the following, which is that take the two Higgs doublet model. So people have matched it to SMEFT, but they always work in the decoupling limit, right? Which assumes that the other doublet mass squared is large and positive, which means, of course, it doesn't acquire a VEV. But you can easily see, and this EFT submanifold language is really good language for seeing this distinction, that if the second, basically if both Higgses have negative mass squareds, then of course you can have a totally perfectly physical spectrum. But indeed, that EFT, if you integrate out the heavy degrees of freedom, must be HEFT. And so one of the things we're working on now is trying to come up with the sort of ideal distinction in a two Higgs doublet model between when you have to use HEFT and SMEFT. Because again, currently all the SMEFT is very far in the decoupling limit. And there are some bases in which you can do this integrating out, where SMEFT is still good as you come away from the decoupling limit. But of course, once both doublets get VEVs, you have to use HEFT. And the same is true indeed in the triplet example. And this actually turns out to explain some disagreement in the literature about the EFT of a heavy triplet. Are
there some disagreement? I don't know much about
it's a very
literature.
It's a very subtle disagreement. So the disagreement is basically, there's a long literature by Sally Dawson and collaborators, and then there's another EFT literature by Vitek Skiba and collaborators. And so the Skiba, they integrate out a triplet in SMEFT, and then they find perfect decoupling. Whereas Dawson collaborators in their papers, they work in the mass eigenbasis, and everyone's doing this at one loop, and they find a non-decoupling effect. And it turns out what's at the heart of the distinction is that by working at one loop, there's a one loop tadpole. That means that in the Dawson work, the one loop tadpole for the triplet means there is always a little bit of extra electroweak symmetry breaking for the triplet. And so of course, if you integrate out, it must be a HEFT and is non-decoupled.
I see.
So that turns out to be the answer. So yeah, there's a nice way to understand all of these examples with this picture. And so we're hoping to develop that a little bit further as well.
Okay, so one more question. So you know that nowadays people are trying to, derive some constraint on, the information on the Wilson coefficient of the dimension 6 operator in SMEFT from the LHC high energy collision data, right? For example, tab EFT and so it's kind of, it's a subgroup of the SMEFT. So so what is your opinion to use SMEFT to,
I think coming into this project, I believed that SMEFT was the only thing that made sense, right? Just for sort of intuitive reasons that we started out with. And it's also much simpler, right? It's a much cleaner parameterization, and we know a lot more about it. But I think to me, the conclusion at the end is we know absolutely, of course, as long as we're measuring zero, right? As long as we're measuring standard model, it doesn't matter. But the moment you measure a deviation, there is no reason not to use HEFT. And indeed, if the deviation is due to anything that's within an order of magnitude of the weak scale, HEFT is going to allow us to figure out most quickly what is the actual underlying physics. So Dave, I think this week is giving a talk to one of the EFT working groups to try to get this message across.
I see. Yeah. You mean at the SNOMAS meeting next year?
Oh, no. He's actually, so there's the LHC EFT working
few days ago, there was a EFT workshop at SON, right?
Yes. So it wasn't that one, but he's trying to get the message across to the LHC EFT working group.
I see.
This is important. SNOMAS, I have a different role in SNOMAS, so I'm not going to be pushing my own work, but this is also an interesting thing for SNOMAS. There's just to follow up, SMEFT has lots of amazing properties, like there are these surprising zeros in the matrix of anomalous dimensions.
Mm-hmm.
And that turns out that has
right.
to do with helicity selection rules. We know
Right.
almost similar things should be true in HEFT. We just haven't
Right.
studied them yet, right? So there's a
so.
whole lot of interesting formal questions as well
I see.
that are worth asking.
Professor, here is Wagner from Kies. I have a question. On the other hand, although, as you said, that HEFT might be the appropriate way to parameterize new physics is depending on the scenario and so on, but we lose the constraint that is connected to the symmetry in the potential, right? In the SMEFT case, which is more stringent than in the HEFT case, which means that we would, since we don't have such a stronger bounds to constrain the functional form of the operators in this case, in this example, this means that we would have a much larger set of parameters to fit. Is this correct?
It is. Now, I should say, there is still power counting in HEFT, but they're at the leading non-trivial order. There are, as you say, many more operators because there are fewer symmetry relations. So practically what this means, of course, is, if you work to a certain order in the EFT, and there are more operators, and you have a finite set of measurements, and then you marginalize to figure out your constraints, you're going to have weaker constraints, right?
Yes.
And it's just going to be more of a pain. You have more flat direction. So that is, of course, the trade-off. That's absolutely the trade-off. And I think before doing this work, I would have said, yeah, okay, maybe HEFT is some crazy strong dynamics that, break electroweak symmetry. It's like, it's a composite Higgs model or something. Maybe I need HEFT for that. And it doesn't look like that's true, so SMEFT is the right idea. But I think now the point that if you just have a scalar that gets a singlet, standard model singlet, right? It's not breaking any standard model symmetries. It has no interesting VAVs. But if it's getting appreciable amount of its mass from electric symmetry breaking, that EFT is HEFT. And to me, that's such a simple and totally consistent scenario with the data, and that EFT must be HEFT. And so I'm not saying you should stop doing SMEFT. Obviously, I agree it's a very concise experimental parametrization, but there's simple situations where HEFT is the only way to understand the data. And so we should at least expand our effort accordingly.
I see. Okay, well, so which means more or less that it may be more appropriated often in a top-down approach, like an EFT or a top-down approach, where if we try to just do a power counting and build all the set of operators, this wouldn't provide accurate information about new physics and so on, as a way to, as I said, just doing a global fitting in this case would require a large amount of processes and a large amount of freedom as well to fit them.
It's true, but I would put it a different way. If you're going from the top down, you have a model and you want to map to EFT. My statement that HEFT converges faster if the thing is near the weak scale means that although there are more operators at a given order in power counting in HEFT, you don't have, in SMEFT, you have to go to higher orders in power counting to reproduce the real physics. And so there's actually a trade-off where, because of that, HEFT could actually, at the end of the day, require fewer parameters to match between the data and the UV theory. So it's a sort of a, it can be a little surprising that HEFT could be more appropriate.
Okay, maybe just one more question, probably too naive, but this discussion and this distinction is strictly connected to the physics of the potential, right? Which means that in some sense, you preserve the paradigm of standard model symmetry being present in all sectors other than the potential, which means that the assumption is that the potential may present a symmetry which is either larger or more general than the standard model one. But on the other hand, in general, we test, and of course, this could be seen also in the properties of gauge vector, the gauge bosons and so on. On the other hand, we usually test this through fermions, right? Like through fermion interactions and so on, which is still connected to the standard model in some sense. Yes, what I mean is that there is still this paradigm that any UV theory should contain the standard model gauge group at some level in their breaking pattern.
Yes. Yes.
And this, but this could be, or this might be not true in the potential, in the physics of the scalar potential. So, on the other hand, we test this physics through fermion interactions, which is, so there is any contradiction on that or no?
No. So maybe I can draw, let me draw a continuous line through the logic. So indeed, in all these cases, the assumption is the UV theory respects SU2 cross U1. And so now the question, which I've been trying to answer in this talk, is how do you get from such a UV theory to an EFT that only respects UN electromagnetism, which is HEFT, right? How does that happen? And the answer is either something else apart from your light degrees of freedom broke the symmetry as well, that you integrated out, or there is a field that you integrated out that becomes massless somewhere on your EFT moduli space, and so you have to bring it back in. Now, both of those scenarios, I've focused on the consequences for the potential in the EFT. I've actually also not just the potential, that's the zero derivative bit, right? The geometry is encoded in the two derivative bit. And so the lesson is things show up both in the zero and two derivative sectors, okay? Those are sort of universal properties because whatever is happening in the UV to get to the EFT, it's going to leave its imprints there. But if the UV physics that you integrate out also couples to fermions, then in fact, you will also see similar pathologies in operators involving fermions. And so you could measure it there as well. But it depends a little more sensitively on how you couple to those, okay? The last thing just to say is this whole question of unitarity violation, indeed, it's something we primarily measure in, say, vector scattering or in Higgs scattering. But of course, you can also measure unitarity violation in the longitudinal scattering of longitudinal vectors into top quarks. And that is actually also sensitive to the effects that I've described here.
Thank you. Thank you.
Okay, any other question? If not, then let's thank the speaker again.
Okay, thank you very much.
Thank you very
Thank you
much.
so much. Thank you for having me. It was a huge pleasure. It's good to see all of you.